What is displacement thickness? See, it is defined as the distance perpendicular to the boundary by which the boundary should be displaced to compensate for the reduction in momentum due to the formation of boundary layer. So it is denoted by delta star. So let us see what is displacement thickness in detail. Let us take a flat plate above which there is a fluid flow. So you can see the streamline here, and let the height of this uh, streamline from the boundary is delta. So between this streamline and the boundary there is a fluid flow. So this fluid flow will be like this, and the flow rate through here, through this section 1, actually is equal to m dot, that is found using m dot, that is equal to rho into area of cross section into velocity. So that is equal to, here this free stream velocity is actually is equal to u infinity, and this width of the plate is b, and the height here is delta. So b into delta is the area of cross section, rho is the density, u infinity is the free stream velocity. So this can also be written as rho u infinity b dy integral 0 to delta. So this vertical height is this is the y direction. So you can take this as dy. So if you integrate it, you will get this. So this can be written like this. So the mass flow rate through section 1 is integral 0 to delta rho u infinity b dy. And here also you can see that the mass flow rate is integral 0 to delta rho u infinity b dy. So this is the streamline, top streamline. There is a mass flow, fluid flow here like this. Thickness is delta. Now let us take another case. So the first case here is without boundary layer. This is without boundary layer. Now we will take the case with boundary layer. With boundary layer. So this is a flat plate, and you can see there is a boundary layer growth. So this is the boundary layer growth. First here it is 0, boundary layer thickness is 0. It goes up to here, the say uh, the boundary layer thickness keeps on increasing, and the height of this boundary layer thickness, the boundary layer thickness at the end of the plate is delta. And we are taking two sections here, 1 and 2, and on the top of it there is a streamline. Between this streamline and boundary there is a fluid flow like this. Now what is the mass of fluid entering here at section 1? That is, previously we have seen that this is equal to rho into u infinity, there is a velocity here, into b dy integral 0 to delta. So mass entering here, and this is the mass leaving here. Note that at this section 2, the velocity is u, it is not u infinity. Velocity is small u, because of the formation of the boundary layer, velocity here gets reduced. Inside the boundary layer is different. On the top it is u infinity, but inside the boundary the velocity is u, and this u is less than u infinity. And rho u infinity b dy is greater than rho u b dy, integral 0 to delta. because the mass flow rate here will be more than the mass flow rate here, because u is less than u infinity. The rest all remains same. So what happens to the rest of the bond? See, since this mass flow rate is greater than this one, what happens to the rest of the mass flow? So this streamline, to accommodate that, this streamline gets shifted upward. Okay, this is the new streamline. So this is the new streamline. It gets shifted up. So actually the flow slightly gets shifted up. Earlier the flow was completely horizontal in the x direction. Now it has got a component in the y direction also. And it gets shifted by a distance of delta star. And this is the displacement thickness. And this is the displacement thickness. So now let us look at this definition. So it is defined as the distance perpendicular to the boundary. See, this is the boundary, perpendicular to the boundary, by which the boundary should be displaced to compensate for the reduction in, actually it is reduction in mass flow rate due to the formation of the boundary layer. So it is denoted by delta star. So you can see that there is a reduction in the mass flow rate to, so this delta star is the distance perpendicular to the boundary by which the boundary should be displaced to compensate for the reduction in mass flow rate due to the formation of the boundary layer. So actually this will be the mass flow rate through this layer, that is rho u infinity b delta star, because here the velocity is u infinity. This is the free stream velocity. Free stream velocity, and b is the thickness of the plate, and delta star here is the height. So u rho u infinity b delta star. So you can see that this rho u infinity b dy, that is here is the mass flow rate here, will be equal to rho u b dy integral 0 to delta, that is the mass flow rate here, plus this mass flow rate rho u infinity b delta star. If you solve this, you will get delta star. If you take it to the left side and solve it, it is simple. Delta star is equal to 0 to delta 1 minus u by u infinity into dy. So this is the expression for finding the displacement thickness. What is momentum thickness? Momentum thickness is just like the displacement thickness. It is defined as the distance perpendicular to the boundary by which the boundary should be displaced to compensate for the reduction in momentum due to the formation of boundary layer. It is denoted by theta. Let us take the flat plate here. You can see the boundary layer formation on the top of the plate, and thickness of the boundary layer at this position is a delta. And let us take two sections, 1 and 2, this 1 and 2, and you know that the flow gets shifted slightly upward to compensate for the reduction in mass flow rate. We have seen the derivation in displacement thickness. So this is the mass flow rate flowing through here, that is integral rho b. B is the thickness of the plate, u is the velocity at each section, and it into dy integral 0 to delta. This same mass flow rate, okay, the same mass flow rate is flowing through here, this section. Now this streamline gets slightly shifted up, okay, because to accommodate for the mass flow rate. Now let us try to calculate the momentum of this mass flow rate. This P is equal to m dot V into V. It is m dot into V, that is mass flow rate into velocity, and this mass flow rate is equal to rho b into delta into u integral 0 to delta into u. This is a velocity, so this is equal to rho b u dy into u integral 0 to delta is equal to rho b u square dy integral 0 to delta. So I have written this is the momentum, is the momentum here, is the momentum at this section 2. Now what will be the momentum at section 1? This is equal to rho bu into u infinity dy integral 0 to delta, because here the velocity is actually u infinity, free stream velocity. That is why we have written it is u infinity. But you know, this momentum rho b u into u infinity dy integral 0 to delta, that is the momentum at a section 1, is greater than momentum at a section 2, and momentum at section 2 is equal to rho b u square dy integral 0 to delta. So to compensate for the reduction in momentum due to the boundary layer formation, the boundary needs to be shifted up. You can see that this is slightly gets streamlined, needs to be shifted up by a distance theta. So this is the distance theta, and you need to find this distance theta, that is equal to, so let us find the momentum through this distance height theta. So rho b theta u infinity square dy, this is equal to rho b theta, this b theta is the area, rho is the density, u infinity square is the free stream velocity square into dy. So this will be equal to rho bu into u infinity dy. So there is a momentum at section 1 is equal to rho bu square dy. There is the momentum here, this is the momentum here, plus rho b u infinity square dy. So if you solve this, you will get the momentum thickness is equal to theta is equal to 0, integral 0 to delta u by u infinity into 1 minus u by u infinity into dy. So let us look at the definition once more. It is defined as the distance perpendicular to the boundary by which the boundary should be displaced to compensate for the reduction in momentum due to the formation of boundary layer. So it is denoted by theta. Let us look at what is energy to be. thickness. It is defined as the distance perpendicular to the boundary by which the boundary should be displaced to compensate for the reduction in energy due to the formation of boundary layer. It is denoted by delta star star. Now let us take a flat plate and see the boundary layer formation over the flat plate. Now the thickness of the boundary layer at the end of the plate is delta. We are taking two sections, 1 and 2. This 1 and 2. And the mass flow rate, this is m dot. Mass flow rate through the thickness delta inside the boundary layer is rho b into u into dy integral 0 to delta. And you know that, see, we have already seen the streamline gets slightly shifted upward to compensate for the reduction in mass flow rate. So this is rho b u into dy. So the same mass is flowing through here. Now see that here the thickness, it is less than this delta. Okay, because the streamline is getting slightly shifted upward. Actually, this same mass flow rate is taken here. Here this same mass flow rate is taken here, but it flows through a slightly narrow region. Now let us find out the energy of the fluid flowing through here. You can see that energy's equation is equal to half into m dot v, half into mv square. So m dot is equal to rho b into delta into u. You have seen that actually it will be 0 integral 0 to delta into u square. This is equal to half into rho b u dy into u square. This is equal to half into 0 to delta rho b dy into u cube. So this is the equation for the energy of the fluid. So I have written that here. This is the energy of the fluid. Now what is the energy of the fluid at a section 1? This is equal to half into rho b u dy into u infinity square, because here the velocity is actually u infinity and the mass flow rate is taken as the mass flow rate is section 2 itself, rho b u dy. And you know that the energy at section 1 is greater than energy at section 2. So rho b u dy into u infinity square is greater than half into rho b dy into u cube. So let us try to find the energy flowing through this section. You can see that streamline gets slightly shifted up to compensate for the reduction in energy. Look at the definition. It is defined as the distance perpendicular to the boundary by which the boundary should be displaced to compensate for the reduction in energy due to the formation of boundary layer. It is denoted by delta star star. So this is equal to half into rho b into delta star. This is the mass flow rate into u infinity cube. So you can write that here. Half into integral 0 to delta rho b u dy into u infinity cube is equal to half into 0 to delta rho b dy into u cube plus half into rho b delta star star into u infinity cube. On solving this, you are taking this to the left side and solving this, you will get delta star star is equal to u by u infinity 1 minus u by u infinity the whole square into dy. So this is how we derive energy thickness. Let us try to do a problem on displacement thickness and momentum thickness and energy thickness. So look at this problem. Here the velocity distribution in the boundary layer is given by u by this capital U is actually u infinity is equal to 2 into y by delta minus y by delta the whole cube. So actually this is the boundary layer and this is the thickness. And this velocity profile is given by u by u is equal to 2y by delta minus y by delta the whole square. Now you know that by formula you know delta star is equal to 1 minus u by u infinity into dy, integral 0 to delta. If you substitute for u by u infinity from the question, you will get 2 into y by delta minus y by delta the whole square dy. And if you expand the bracket, you will get integral 0 to delta dy minus 2y by delta dy plus y by delta the whole square dy. And so delta star is equal to y minus y square by delta plus y cube by 3 delta square within the limits 0 to delta. So you will get delta star as delta by 3. So this is the displacement thickness. This is how you find the displacement thickness. Now let us see how to find the momentum thickness. So the formula for momentum thickness is integral 0 to delta u by u infinity into 1 minus u by u infinity dy. And if you substitute here, it is quite lengthy, but if you substitute here, you will get like this. 2y by delta minus y by delta the whole square, 1 minus 2y by delta minus y by delta the whole square, again bracket, into dy. So if you are simplifying it, you will get it like this. So on solving this is quite lengthy, and if you solve this, you will get the answer as 2 delta by 50. And now let us find the energy thickness. So energy thickness also, you can substitute the equation. You know the equation is u by u into 1 minus u square by u square. So if you substitute it here and solve, you will get the final equation as 22 delta by watt naught 5. So this is how you find the energy thickness, displacement thickness, and momentum thickness.